Hello guys, how are you today? So today I'm going to be explaining top question 11, 12 and 13. We start with 11. A solid ball of diameter 4.2 centimeter. It's important to always change to meter. So 4.2 times 10 to the power of minus 2 meter. Is made from a material of density 7.2 gram per centimeter cubed. You don't keep it in gram per centimeter cubed. You need to change it to kilogram per meter cubed. Now, how do we change it? You just change it by multiplying by 1,000. So you just need to multiply by 1,000. You will get 7,200 kilogram per meter cubed. Now, what do they want us to find? They want us to find the weight of the ball, or no, they want us to show that the weight of the ball is 2.7 newtons. What do we know? We know that W is equal to mg. I have G, which is 9.8. And M is equal to what? Is equal to the density times the volume. So let me find the volume of this solid ball. So what do we need to apply? We know that the ball, the volume of the ball is 4 over 3 pi r cubed because it's a sphere, right? So it's going to be 4 over 3 pi. The radius is the diameter divided by 2, so 2.1 times 10 to the power of minus 2 times 2.1 times 10 to the power of minus 2, all of it to the power of 3. Okay, so now it's gonna be the density, which we found it to be 7,200, times the volume, which is 4 over 3 pi times 2.1 times 10 to the power of minus 2, all of it cubed, times what? Times 9.8. Put it on the calculator. And this would give me my answer to be approximately 2.73, but they want to show that it's 2.7, so you round it and it's what? It's 2.7 newtons, okay? We move on to part B. The ball in A is hung from the end of A, okay, of a non-uniform bar AB. So they showed us the diagram. Okay, so it's a non-uniform bar, meaning that the weight would not be at the center. The bar has a length of 100 centimeter and a weight of 4.60 newtons. Its center of gravity is 40 centimeters away from B, meaning that it's also how much away from A? It's 60 centimeters away from A. The bar is pivoted at P. The pivot is 10 centimeters from B. An object X is hung from the end of B. The weight of X is adjusted until the bar is horizontal and in equilibrium. Explain why the center of mass and the center of gravity are located at the same point. So what we need to know is that the gravitational field is uniform, meaning that G will be the same everywhere. For example, what did they do? They said that for one ball, if you try to find the center of mass, it would be sigma RI over mi, right? If you try to find the center of gravity, it would be over sigma mi. If you try to find the center of gravity, it would be sigma RIMIG over sigma MIG. So the only thing we added up and down was G. They will cancel and they will give you the same exact thing, meaning that they are the same. So you can say gravitational field is uniform. G will be the same everywhere. Now, number 2, calculate the weight of X. Okay, very important. We need to apply what? We need to apply sigma torque is equal to 0, meaning the torque clockwise is equal to the torque counterclockwise. So let's take our rotational point to be the pivot over here because we have the distances, right? And we said this distance here was how much? Was 60 centimeters, right? Okay, now we can apply T clockwise is equal to T counterclockwise. We first start by finding the clockwise and the counterclockwise. We first need to draw the force of B, which has the mass over here, so it's downwards, the weight. So now what do we need to do? What do we need to do? We need to identify which is the clockwise and which is the counterclockwise. If I do that, I will see that my clockwise, according to the right-hand rule, is this, and my counterclockwise, according to the right-hand rule, is this. So what does this mean? This means the torque of the clockwise is equal to the torque of the counterclockwise. What's the torque of my clockwise? It's the weight of X multiplied by the perpendicular distance from the pivot, which is 10 centimeters. It's equal to Now, the torque counterclockwise, meaning this 4.6 Newton multiplied by the distance of the force from the perpendicular distance, which is 40 minus 10, which is how much? Which is 30 centimeters. So 4.6 times 30 centimeters plus what? Plus 2.7, the force, 2.7 newtons, multiplied by what? Multiplied by the perpendicular distance till here. So that's going to be 60 plus 30, which is how much? Which is 90 centimeters. So 60 plus 30, it's how much? It's 90 centimeters. Now, because we're making them equal, we do not need to change their units into scientific units. You can just multiply. So you will get 10W is equal to 4.6 times 30 plus 2.7 times 90, which is 381. So you will get the weight to be 38.1 newtons. That's it for question number 11. We'll move on to question number 12. A uniform beam AB is attached by a hinge to a wall at the end of the figure. Right, as shown in the figure below. The beam has a length of 0.8 meters and the weight of 20 newtons. A block of weight W rests on the beam at a distance 0.2 meters from end A. So the beam is held horizontal and in equilibrium by a support attached between the end of B, okay, and the wall at fixed point C. The string is at an angle of 30 degrees to the horizontal. The tension in the string is 80 newtons. They said, part A, explain why the weight acts at a point 0.40 meters from the beam's end of A. So look, very important. The weight, okay, is of a uniform beam, meaning it will be exactly at the center of the object. If the length of the beam is 0.80, the weight will be exactly at the center of it, exactly at half of it. So this will leave how much for us here? It will leave for us 0.40 meters from A. How did they explain it? They explained it by saying the beam is said to be uniform, thus its center of gravity is at its geometric center. The center of gravity is a point from which the force of the weight acts on the object. That's all you need to say and you will get the point. Perfect. Now part B, show that the vertical component of the tension in the string is 40 newtons. Let us calculate the vertical component. We know this is the vertical component, this is the horizontal component. They want us to resolve and they want us to only find the vertical component of the tension. What's it gonna be? It's gonna be, if you draw a parallel, you will see that it's opposite to the angle, so it's gonna be 80 sine 30, which is how much? Which is 40 newtons. What are they asking in part C? By taking moments about the hinge, calculate the weight W of the block. Perfect. So they said take this as what? As your center of rotation. So if I draw my resolved tensions again, I will see that this is R. I need to resolve it into what? Into Ry and Rx. Okay, perfect. And then I have my block with the weight. And then don't forget about the normal push. Actually, they didn't take into consideration the normal push, so don't take it into consideration in this scenario, okay? So, if we choose the center of rotation to be at point A, we are getting rid of how many forces? We're getting rid of Rx, we're getting rid of Ry, and we're getting rid of the horizontal component of the tension. So the only forces we have left are this force, which is 40 newton, the vertical component of the tension, this force, which is 20 newtons, and the weight. Now what do we apply? We apply sigma torque is equal to 0 about any point, right? So I do the right hand rule. I'll see which ones are clockwise, which one are counterclockwise. Then I say torque counterclockwise is equal to the torque clockwise. The only torques clockwise are the weight and the 20 newtons, right? So it's gonna be the weight of the block multiplied by the distance from W to A. How do I know the distance? They gave it to us in the beginning. It says block W rests on the beam at 0.20 meters, right? So W times 0.20. In addition to what? In addition to the 20 multiplied by the distance, which is how much? Which is 0.40. How do I know? Because this is the weight of the beam and the beam is uniform, so it's gonna go exactly at the center of gravity of the exactly at the geometrical center of the beam, so it will cut it into two equal parts, so 0.40 and 0.40, so this is 0.40, and then my torque counterclockwise is only 40 newtons acting on it, so 40 times the perpendicular distance, which is all of it, which is 0.80. Perfect. Now we need to solve. Move this to the other side. You will get that 0.20 W is equal to 40 times 0.8 minus 20 times 0.4, and you will get it to be equal to 24. So W is equal to 24 over 0.20, and W is equal to 120 newtons. Part D, it says, deduce the magnitude of the force exerted by the hinge on the beam. Okay. Explain whether this change... Oh, sorry, this is in part E. The block is now moved towards the end of B, okay, of the beam, and the system remains in equilibrium. So we know that it is in equilibrium, right? And we separated it into R, Y, and R, X, and we don't forget about the tension. So this would be 40 because it's 80 sine 30, and the other one is 80 cosine 30, which is 40 radical 3. And we have the value of the weight to be 120 newtons. Now what can we apply? We used sigma torque is equal to 0 about any point. Now we can use sigma force is equal to 0. That means everything up equals everything down, and everything left equals everything right. So let's start with everything up equals everything down. It's gonna be 40 plus Ry. Right, 40 plus Ry is equal to 120 plus 20. So after solving, you will get Ry is equal to 100 newtons. We found Ry, we can now find Rx. Everything left equal everything right. Rx is equal to 40 radical 3. By the way, in the answer key, they're wrong. I don't know why they said that tension X is equal to Rx. We know that tension X is how much? We know that the tension X on the X-axis would be 80 cosine 30. So I don't know why they did 40 cosine 30, but it's supposed to be 80 cosine 30. But anyways, please do double check with your teacher, because as far as I know, it's supposed to be 40 radical 3 because you do 80 cosine 30. So now, what are you going to do? You're going to find resultant R. It's equal to radical Rx squared plus Ry squared. So you put it on the calculator. Radical 100 squared plus 40 radical 3 squared. And you should get your value of R to be equal to 122 Newton. Okay, so that is it for part D. Now we continue reading. It says the block is now moved towards the end of the beam, and the system remains in equilibrium. Explain whether this change will increase, decrease, or have no effect on the tension of the string. As the block moves toward the string, it exerts a greater clockwise torque on the beam because the distance becomes greater. Because what is the torque? Torque is force times perpendicular distance. The force stays the same, but the distance is changing. It's increasing because we're going farther away from A all the way till B. So it will exert a greater clockwise torque on the beam. Okay. Thus, the counterclockwise torque on the beam must increase, and the force of tension must also increase because the string stays in the same position. So if for the weight the force stays the same but the distance increases, and this is the clockwise torque, and for the tension it is what? It's in a constant distance. What will happen to the force though? It will need to increase, so that's what will happen. We will have a greater tension. That's it for question number 12. We'll move on to question number 13. Yalla, let's see. State two conditions for equilibrium. You can say sigma torque about any point is equal to 0. Very important to say about any point. And then sigma f is equal to 0. This is the equations. If you wanted to state, you would say that the rotational equilibrium is attained when a net torque about any point on an object is 0. And for the translational equilibrium, it is attained when a net force on an object is 0. This is how you state them. Now, A bicycle pedal consists of a cycle pedal attached to a uniform crank arm in contact with the chain ring that can rotate about its axis of rotation. The weight of the crank arm is 5 newtons and its length is 30 centimeters. The cycle pedal is of weight 4 newtons. A child is pressing on the pedal normally to the pedal, okay? The plane of the pedal makes the plane of the pedal makes an angle of 30 degrees with the vertical. Anyways, they said in part B, calculate the moment of the crank arm's weight about the axis of rotation. Very important. They said that the crank arm is uniform, a uniform crank arm, meaning the weight is going to be at the geometrical center over here. How much is the weight? It is 5 newtons. And what is the length of the crank arm? It's 30 centimeters. So that means this would be 15 centimeters and this would be 15 centimeters. Where's the axis of rotation? This is my axis of rotation. They want the moment of the crank's arm weight about the axis of rotation. So here you need to do what? You need to do the force, which is 5, times the perpendicular distance, which is 15 centimeters. But don't forget to change it into meters by dividing by 100. So 5 times 15 divided by 100, that is 0.75 Newton per meter. We move on to part C. If the total torque on the bicycle is 20 newtons, what is the force F exerted by the child? Okay, very important. They told us that the total torque, the net torque, is 20. It's not 0, so it's not an equilibrium anymore. So the net torque, okay, it's equal to what? It's equal to the torque clockwise, to the torque counterclockwise, in addition to the torque clockwise with all of their signs, okay? Here, because they're not equal, you have to use their signs. So now what do we apply? We apply that 20 Newton per meter is equal to what? Is equal to the torque that's counterclockwise plus the torque that is clockwise. Don't forget about their signs. So anyways, it has the same weight, right? So we have quite literally the same force of the torque from the center. What does this mean? This means that the torque, okay, of the weight is how much? Is 0.75 Newton per meter. We found it in the previous example. Perfect. Now, what do we have about the cycle pedal? The cycle pedal has a weight. The weight is of 4 newtons. If you go up and you read, you will see that it is of 4 newtons. And it also has a force F extended like this. We need to find the value of the force F, okay? So what can I say? I can say that the weight of the cycle pedal is perpendicular, right, to the crank arm. What does this mean? This means it's perpendicular to the center of rotation. So it's gonna be the force, right? So the torque of the weight. So I'm just gonna write here torque of crank arm. It is what? Crank arm weight. It's 0.75 Newton per meter. Now, torque of the cycle pedal weight. It is what? It is the force multiplied by the perpendicular distance. It's perpendicular to the center of rotation. And how much was the distance of the crank arm? It was 30 centimeters. So how many meters? So 0.3 meters. So 4 times 0.3 meters, okay? And then last but not least, what is the torque of F? Torque of F, it's equal to the force F multiplied by the perpendicular distance, which is 0.30, first of all, times the sine of the angle. What's the angle? If you see over here, this is the weight, right? So this is how much? This is 90. What we also know is that this and this are 90 degrees. So if this was 30 degrees over here, how much is left? It's gonna be 90 minus 30, which is 60 degrees. Perfect. Now I have this interior angle. Not this interior angle, this angle over here. We need to add it to this 90 degrees to get the total angle made with the axis of the center of rotation. So what's it gonna be? It's gonna be 150 degrees, because 90 plus 60, so it's gonna be F times 0.30 times sine 150. So 20 Newton per meter is equal to 0.75 Newton per meter plus 4 times 0.3, which is 1.2, plus 0.30 times sine 150, which is 0.15, so plus 0.15 F. Now we move them to the other side. What do you get? You will get that it's gonna be 20 minus, what is 0.75 plus 1.2? 1.95. So 20 minus 1.95 is equal to 0.15. F, what is 20 minus 1.95? It is 18.05. So 18.05 is equal to 0.15 F. So then F is then equal to 18.05 over 0.15, which is what? Which is approximately 120 newtons. So the force F is approximately 120 newtons. Part D says, will such a bike be easier to ride? Yes or no? So they're saying, if you look now, they said, assume now that the crank of the arm is the same weight but in the shape of a trapezoid. Will the bike be easier to ride? Yes or no? Now, if it's in the shape of a trapezoid, right, the center of mass is gonna be located closer to the axis. So where would my axis be? It would be over here, right? So it's at a shorter distance, right? So because it's at a shorter distance, what would happen to the force? We would require a greater force. So the force will increase, right? Okay, so they said in part D, assume now that the crank arm is of the same weight but in the shape of a trapezoid. Will such a bike be easier to ride? If it's in this scenario, what will happen to the weight? The weight will be, or like the center of gravity, will be closer to the axis. If it's located closer to the axis, and it's the same weight, by the way, it's still the same weight, but closer to the axis, so a shorter distance, what will happen to the torque? The torque decreases. If the torque decreases, then what will happen to the cyclist? The cyclist must exert a larger force because it will be harder for us to rotate it because the torque decreases, it's becoming smaller. So he'll need to exert a larger force to get the bicycle in motion, making the bicycle harder to ride. So that's it for this video. Thank you guys for watching. I hope you enjoyed and have a wonderful day.